All right, so now that we know how to solve 2 by 2 systems, let's talk about some general properties that we're going to rely on, not only for 2 by 2 systems, but for larger systems. All right. So we mentioned that solving by graphing wasn't the best method of solution because our graphs had to be accurate and all that kind of stuff. But what graphing does tell us is it tells us what kind of solutions we can have and we can expect to have. So here's a fact that you need to remember for linear systems. There are three situations. All right, so there are three outcomes when you're solving linear systems of equations, and this doesn't matter uh, whether it's 2 by 2, 3 by 3, 5 by 5, 100 by 100. There are only three things that can happen. One thing, and this is kind of the nicest thing, is if we just get one solution. Now what that means is if we use the 2 by 2 case and we think graphically, one solution happens when we have two lines that intersect once. And of course, two lines are going to only intersect once, at most once, unless there's some degenerate cases, but there it is. So that's the 2 by 2 case. Now, in the 3 by 3 case, we could have one solution. In that case, we're not talking about two lines intersecting, we're talking about three planes intersecting. But we don't worry about that. We just rely on the fact that we could have one solution. That could be one of the outcomes for any size of linear system. Okay, the other outcome that we could get is zero solutions. And it's easy to see that in the 2 by 2 case, what that would mean is you've got two equations that are parallel. They never intersect. In that case, we often say that the solution set is empty. Right? Our good old null solution set. Again, remember, these are the three outcomes for all linear systems of all different sizes. Okay? The third thing that can happen is we can have an infinite number of solutions. How does that happen? Well, that happens if when you go to graph your two equations, let's do it this way, you graph one, and then you graph the other, and they land right on top of each other. In other words, they're basically the same two equations, and so they have an infinite number of intersection points. And so those are the three things that can happen when we solve linear systems of any type, and we'll bank on those three outcomes as we move forward. All right. So be aware, those are the three things that can happen. Now let's talk just a little bit about some terminology here. First of all, these two, if there are any number of solutions, then we call the system consistent. So both of these are consistent. That makes this one inconsistent, right? Inconsistent. Yes. All right. The other terms that we'll use. This is a dependent, or sorry, this is independent, and both of these are dependent. So sometimes we'll be talking about whether they're consistent or inconsistent. Sometimes we're worried about whether they're dependent or independent. All right, and so there we go. So we've already seen the one solution case. How do we know if we have one solution? Well, we solve the system and we end up with a pair, an ordered pair, or we end up with one solution. Okay. What about no solutions? How do zero solutions happen? Well, let's just look at a system. Say this one right here: 2x plus 6y equals 4, and 3x plus 9y equals 11. Now, you don't really see anything right away that maybe indicates that has zero solutions, so you just solve it, right? You just jump in and solve it like any other system. If it's the one solution case, you'll just end up with a solution, 2 minus 3 or whatever. But what's it going to look like if there are zero solutions? Well, we don't know going in, so we just proceed like normal. Let's say we're going to use elimination. So we'll multiply this one by 3 and this one by 2. And that's going to give us two new equations. 6x plus 18y equals 12. And minus 6x, there's the elimination that's going to need to happen, minus 18y equals minus 22. And so when we go to add those, look what we get. We get 0x plus 0y equals negative 10, or just 0 equals negative 10. And so what happens is you end up with an absurd equation. 0 never equals negative 10. That tells you you've got 0 solutions. Moving kind of on up, back up in here to consider what happened. Notice what happens in the elimination process. These all got eliminated, but this side did not. All right, so basically if all of your variables get eliminated with one elimination, but your right hand side does not get eliminated, it's a non-zero number, you're going to end up with some absurd equation. 0 equals negative 10 or 0 equals 7. That tells you you have 0 solutions. In the 2 by 2 case, that would tell you you've got two parallel lines. All right. In the 3 by 3 case, that can actually happen several ways, right? In 3 by 3 case, the graphs are planes. And so the planes might all three be parallel, right? So if I'm looking at our planes from a sideways view, let's try that again. If I'm looking at them, we'll just sketch this in. This is going to be kind of ugly, right? But if I'm looking at them from a sideways view, do not do that to me. So there's our three-dimensional axis. My first plane, might look something like this, right? There's my first plane, a 3, and then my second plane would be parallel, right? It's just below it. My third, or I guess below it in this picture. My third one is parallel to the other two. So see, there's no place where all three planes intersect, right? So that's how that would happen in the three-dimensional case. Or if you looked at your planes, or another way that could happen is you could have a plane there, a plane here, and a plane here. So there are some intersections between any two, but not between all three. So there is no place, nothing that it solves all three at the same time. All right. So we don't get much into the actual graphing once we move from the two-dimensional case, because graphing in 3 dimensions is kind of a pain. But that's kind of how that would work. It's not important that you understand that graphing part of the 3 dimensions, 3 by 3 system, but it does exist, and we will not talk about when you go to 4 dimensions and 5 dimensions. All right, so that's how you recognize when you have 0 solutions for a 2 by 2 case. How about an infinite number of solutions, right? So let's kind of squeeze this one in here. Right, so let's take this system, 2x plus 6y equals 4, 3x plus 9y equals 6. And again, if we just proceed, we're safe to just proceed with elimination. Say we want to eliminate the x's again, right? And that leads us to 6x plus 18y equals 12, and negative 6x minus 18y. And bells start ringing at this point when we see that equals negative 12. So when we add those, look what we get. 0x plus 0y. Boom, all the variables are gone. But look, the right-hand side is also gone. So we end up with 0 equals 0. So if you end up eliminating everything, then you know you have an infinite number of solutions. And the only way you would eliminate everything is if both equations were the same to begin with, right? So if you just look at these two equations, you might say, well, they're not the same, right? Those are my originals. But look, if you multiplied this equation by 1.5, you would get this equation. Okay. So that's how you're going to get an infinite number of solutions. By the way, an infinite number in 3 dimensions can happen if we look sideways at my graphs. There's one plane. I'm looking at it from the side, so it looks like a line. But there's one plane. there's another plane, and they intersect in this line. It's not a point, right? We're looking three-dimensionally straight across the planes. And then if my third plane comes in like that, boy, they all intersect there, and that's a line. That's just one way that can happen. Or all three of your planes could just be the same plane. So again, we don't worry too much about the three-dimensional version, but the important thing to remember is when you're solving any size of linear system, these are the only three things that can happen: one solution, zero solutions, or an infinite number of solutions.